Hello, welcome to Math 251, Calculus 1 here at Cañada College. My name is Lapuz and I'm the instructor for the course. In this video, we will take a deep dive into section 3.9 when we find out what the derivative is of an exponential and a logarithmic function, and then apply those to some of the things that would be useful for us when taking derivatives. First, let's take a look at the objectives. Here we're looking at the derivative of exponential functions and the derivative of logarithmic functions. Now we're going to find the derivative of exponential functions with, again, the use of limits. And the way we're going to find the derivative of logarithmic functions is to actually use the inverse function theorem, because the inverse of a logarithmic function is the exponential function. And we'll also be able to see the exponential function and how there is going to be a special number for us that's going to be based on a limit. And then we're going to use logarithmic differentiation to find derivatives of more complicated functions that involve a lot of quotient rule and chain rule. And then we're going to finally get our final version of the power rule that would work for any real number, and that's going to be based on the exponential functions. All right, first let's dive into the derivative of the exponential function. The exponential function can be defined as b of x, or b raised to the x power, for b that's bigger than 0. And then if we follow through applying the derivative, or the definition of the derivative, we're going to have the limit as h approaches 0 of b of x plus h minus b of x divided by h. Now we do some algebra and factor out b of x, and then we're going to get the limit as h approaches 0 of b of h minus 1 divided by h. Now this, if upon closer observation, this is actually the original function, or the derivative of the original function evaluated at 0. And so there's something interesting about b of h minus 1 divided by h, and as we take the limit approaches 0, depending on what b is. Now ideally, if we can get this thing to equal to 1, that is our ideal situation. So when is this going to equal to 1? Well, it turns out that there's this very special number for b where this limit as h approaches 0 is actually equal to 1, and that is the number e. So e is a very special number in calculus. It's Euler's number. It's approximately 2.7181-ish, something like that. But it is the number where, if you put it as an exponential function, the derivative of it is itself. So that's what it's saying here. Capital E of x, they're just calling that capital E is just the name of the function. If that's equal to e to the x, then its derivative is also equal to e to the x. And this is assuming that the derivative of e to the x evaluated at 0 is equal to 1. And that's that limit that we saw in the previous slide. So this is why this e to the x is a very special number in calculus. It's because this is the only function whose derivative is itself again. So in general, applying the chain rule, we can have something more complicated from x for the value of x, like e to the g of x. And in that case, it would just use the chain rule and say it's going to be e to the g of x itself times the derivative of the inner function. In this case, the inner function is the exponent, which is going to be g prime of x. All right, so that is the derivative of the exponential function, or the special natural exponential function. Now let's use this special natural exponential function and take a look at the natural logarithmic function, its inverse, and find the derivative of that. So it turns out that if you let y equal to ln x, and then you take the e of both sides, so you have e to the y is equal to x, and then take the derivative, then you will have dy dx is equal to 1 over e to the ln of x, which is equal to x. And so here, dy dx is going to be 1 over x. So the derivative of the ln of x function is equal to 1 over x. So that's very important. You go from a logarithmic function to a rational function. And more generally, if you have something more complicated than just ln of x, if you have something more complicated than x, like g of x, the derivative of ln of g of x is going to be 1 over g of x times the derivative of g of x. Or simply, you can write it as one fraction, g prime of x divided by g of x. And that will come up again later, probably in next semester when we're trying to undo the derivative that we're taking. So if we have a derivative in the numerator and the original function in the denominator, then that has something to do with a natural logarithm. So we have the exponential function with a special e to the x, and then we have the natural logarithmic function ln x. So now let's generalize this to say, what if we have 2 to the x or 7 to the x or something like that? Well, it turns out that that limit that we saw is going to be the ln of whatever b is equal to. And so your derivative of let's start with the second one over here. If y is equal to b to the x power, then the derivative of that is going to be b to the x times, and remember there is that limit thing in there. It turns out that if b was any other number, well, it could also be e, but if b was any positive number, then that b, capital B prime of 0 that we saw there, or that limit, will actually go to ln of b. And if b was equal to e, that special number, we know that ln of e is equal to 1, so that's just going to be 1. But anything else, like 2, the derivative of 2 to the x is going to be 2 to the x times ln of 2. Similarly, now if we undo that or use the inverse function theorem, then if you have y is equal to, this first one, y is equal to log base b of x, then your dy dx is going to be 1 over x times, in the bottom, in the denominator, times ln b. Okay, so these two other functions over here add to your set of all the derivatives that you'll have to, remember and use over and over again. So it'd be good to have a list of derivatives handy while you're doing a lot of these problems, so you don't have to always look it up. If you put it all in one page, you have all your derivatives, and over time you'll start to use them more and more, and it'll just become natural. You'll just remember it. Okay, so those are the derivatives of the exponential and logarithmic functions. Now let's get to the idea of logarithmic differentiation. Sometimes it would be good to use it, and sometimes it would be absolutely necessary to use it. It's good sometimes for convenience, but there are going to be times where there's no other way to do it aside from logarithmic differentiation. What is logarithmic differentiation? Suppose you want to try to take the derivative of h of x, and it looks a little bit complicated, but we have some logarithmic properties that might make it look a little bit easier. So what we could do is take the natural log of both sides, and by taking the natural log of both sides, you're going to have ln of y is equal to ln of h. Now you can expand ln of h as needed. Remember, if h of x is a product or a quotient or a combination of products and quotients and powers as well, remember that the natural log changes those products and quotients into addition and subtraction with the logarithms. And so by simplifying or expanding, by expanding the ln of h, you might have a simpler derivative to take. So now we differentiate both sides in step 3, and we note that the left-hand side is ln y, so the derivative of that is 1 over y times dy dx, because you got that dy dx there as part of the chain rule. And then the derivative of the right-hand side would be a bunch of ln functions with chain rules involved. And as a last step, or second to the last step in step 4, since the left hand side is 1 over y dy dx, you want to multiply both sides by y, and then at the very last step you replace y by h of x, because that's what the original problem was. All right, let's take a look at a couple of examples. Here's an example where you absolutely have to do logarithmic differentiation, because your x, your base has an x in it, but your power also has an x in it. So let's take a look at y is equal to 2 times x to the 4th plus 1, quantity, the whole thing raised to the tangent x power. So tangent x is a function. You can't use the power rule here because the tangent x is not a number. Now remember, the power rule works if your power is just a real number, and tangent x is not. So what we're going to do is we're going to take the ln of both sides. So let's go through the algorithm. We're going to take the ln of both sides, and then we're going to expand the right hand side. Now the right hand side has something, ln of something raised to power. We can take that tangent x, that power, as a coefficient of the ln, and so now you don't have a power anymore. So in our second step over here, we have tangent x times ln of quantity 2x to the 4th plus 1. And so that's expanding it, so to speak. And then now you take the derivative. In this case, we have to use a product rule. We have the tangent of x times the ln of that expression. And so it's a derivative of the first, which is secant squared, times the second, plus the derivative of the second, which is going to be, so the derivative of the ln of something is going to be 1 over something. So that's 1 over 2x to the 4th plus 1 times the derivative of 2x to the 4th plus 1, which is 8x cubed. And so they put that together in one fraction, and then you tack on the first function. So now that you have that, you multiply both sides by y to get dy dx by itself. And since your original problem was an explicit function, then you don't want any y's on the left hand side, so you simply replace y with the original function again. And that's it. This is your derivative. It looks pretty complicated, but without this logarithmic differentiation, we wouldn't be able to do this derivative. Let's take a look at another example where we don't necessarily have to use logarithmic differentiation here. But if you look at it, we have a quotient and product and a square root and all kinds of stuff happening. So why not use logarithmic differentiation? Let's give it a try. So in doing this, we would take the ln of both sides, and now we would expand the right hand side. Now look at the second step. When you expand the right hand side, you have the ln of x plus 1/2 ln of something minus x times ln of e, which you could do or not do, and then minus again. So you've changed this original problem with a bunch of addition, or with a bunch of products and quotients, into a bunch of addition and subtraction. And now they decide that they take the derivative of both sides. Remember, the derivative of the left hand side is going to be 1 over y dy dx, and the derivative ln x is 1 over x. The derivative of the next one is going to be 1 over that thing, and then there's an extra 1/2 there. And the derivative of x is just, well, ln e is equal to 1, so we're just taking the derivative of x, which is 1. And then the derivative of 3 times ln of sine x is going to be 1 over sine x times cosine x times 3. Okay. And now we just, second to the last step, we multiply by y on both sides, and in the very last step you replace y by that. Now this probably isn't the function or the form of the function you would get had you done this original function using the quotient rule and the product rules, but these two things should be equivalent, so I think it'd be okay. All right, that's logarithmic differentiation. We finally end this section and this whole chapter by looking at the power rule again. So we're revisiting the power rule. And so remember, at the beginning we saw the power rule that only worked if we had a positive integer. And so if we have a positive integer, and that proof was used, they used the binomial theorem for that proof. And so we have the derivative of x to the n, where n is a positive integer. And then after we studied the quotient rule, we were able to take a look at x to the k, where k is not just positive, but also a negative integer. So any integer, positive or negative now, we have the power rule. And notice it's the same power rule, right? N x to the n minus 1. Here we have k times x to the k minus 1. And then a couple of sections ago, when we started to do the implicit function theorem, we were able to do x to the 1 over n, or x to the m over n. So x to some power where the power is some rational number. And so again, we see the same formula. It's x to the 1 over n. The derivative of that is going to be 1 over n, that original power, x to the 1 over n minus 1. So you subtract 1 from that power, and that happens the same with the second formula here. So we started with positive integers, and then we went positive and negative integers, and then we went to rational exponents. And finally, we get to do this for any real number we want, including e. And so e is not an integer, it's not a negative integer, it's not a rational number. It's one of those things that we call a transcendental number. So is pi. Pi is another example of a transcendental number. So any number that we choose, the square root of 2, which is an algebraic number, but it's not rational. And so that's another example of a real number that we were not technically able to do by using the power rule. And so now this final extended power rule tells us we can do this for any real number we want. So if we have y is equal to x to the r, where r is any real number, whether it be an integer, a negative integer, a rational number, or any other number that's not rational, irrational number, which includes square root of 2, an algebraic number, or e, a transcendental number. So any number that we choose, this should work. And we do this by using logarithmic differentiation. So we take the ln of both sides, we expand, the quote expand is really just bringing the r out in front, and then r is a constant, and derivative ln x is just going to be 1 over x, so you take the derivative of both sides, and then you solve for dy dx, so that's y times r, constant r, divided by x. But what's y equal to? Y is equal to x to the r, and then you have x to the r divided by x, which is essentially x to the r minus 1. And again, the constant r is just going to remain there. So the derivative of x to the r is going to be r times x to the r minus 1. And without logarithmic differentiation, we wouldn't be able to finally prove this final version of the power rule. All right, so that is the logarithmic and exponential differentiation, and that's why these things are important. And this wraps up our last section in this chapter. And so now we should be able to take the derivative of almost any function that we run into. And so some complicated functions, you might need logarithmic differentiation. We know how to take the derivative of the inverse trig functions and inverses and things like that. So just about any function we can think of, we should be able to take the derivative of that. All right, you did it. You've gone through the last section in this chapter. We're on to applications in the next chapter. But for now, let's keep on working on this and make sure that we're understanding and internalizing a lot of these things. Good luck.